Good evening and good morning to our audience in Asia, including our speaker, Dr. Yuan, joining from Shanghai. Thank you so much for joining us very early in the morning. I'm Gi-Yuk-shin, Director of the Shorenstein Asia Pacific Research Center. And this is the last of our 4 webinar series, Perfect Storm, Climate Change in Asia. So we began our seminar series, by talk, from UN Secretary General, our former Secretary General Ban Ki-moon. So if you missed it, you can watch it online in our website. So throughout this 4th quarter, our speakers have been discussing the climate change impact and risk in the Asia Pacific region, adaptation and mitigation strategies, and policy responses. So we have focused on specific geographic area or thematic issue, and today is on healthcare policy. So I'm very happy to introduce you to my colleague, Dr. Karen Eggleston, who directs our Asia Health Policy Program. So Karen will be introducing our speakers today and also moderating the discussions to follow. So thank you again for joining us today, and please enjoy. So Karen.
Great, thank you, Gi-Yuk, and thank you all for joining us today. I'm thrilled to introduce our 2 special guest speakers today, Professor Carleton and Professor Yuan, to share their detailed research with their other colleagues on the global mortality consequences of climate change, implications for Asia, and a case study on local adaptation policy from Chengdu, China. Professor Tamma Carleton is Assistant Professor of Economics at the Bren School of Environmental Science and Management at the University of California, Santa Barbara. Her research combines economics with data sets and methodologies from remote sensing, data science, and climate science to quantify how environmental change and economic development shape one another. She's an active member of the Climate Impact Lab, an interdisciplinary team conducting an empirically grounded global assessment of climate change impacts, and a lead author of the study they will be discussing today. Tamma joined the Bren School after a postdoc at the Energy Policy Institute at the University of Chicago. She holds a PhD in agricultural and resource economics from the University of California, Berkeley, and master's degrees in environmental change and management, as well as economics for development from Oxford. Next, we have Professor Jiacan Yuan. Yuan is an associate professor of climatology at the Department of Atmospheric and Oceanic Sciences at Fudan University in Shanghai, China. She is interested in understanding fundamental dynamic processes of the climate system and climate models to improve predictive power and provide more accurate risk assessment of the changing climate. Jiacan's current work focuses on understanding the physical processes and uncertainties in climate changes, and she's also an active member of the Climate Impact Lab. Before joining Fudan University, Jiacan was an assistant research professor at the Department of Earth and Planetary Sciences at Rutgers University. She holds a PhD in meteorology from Peking University. After their presentation, we will have some time for discussion, so please enter your questions in the Q&A function on Zoom. Tamma and Jiacan, thank you for sharing your research with us today. Over to you.
Great, I'll start us off. Thank you so much for the invitation to be a part of this series. We're really excited to share this work with you. Jiacan and I will be both presenting on our joint work that comes out of the Climate Impact Lab, where we are an interdisciplinary collaboration of economists, climate scientists, computer scientists, where we're working to build data-driven estimates of what climate change will look like across the globe. And today, of course, we'll be talking about health consequences, in particular, the mortality impacts of climate change, and a focus in, of course, on the Asian region. So the big, broad motivating challenge for our work is the simple fact that mitigating greenhouse gas emissions is expensive. We've all looked at many graphs that look like this, where we see different climate futures under different emission scenarios. And while we'd all like to be on that lower green line that shows a lower climate risk future, we have to acknowledge that mitigating emissions to get there is expensive. And importantly, it requires us to divert resources from other really valuable social outcomes that we care about, like mitigating poverty, investing in our healthcare systems, investing in our educational systems. And so this simple fact means that policymakers are left having to trade off the costs of mitigating greenhouse gas emissions against the many different benefits of a lower climate risk future, all of the avoided damages from climate change. This is an apples to oranges comparison. And so what we at the Climate Impact Lab focus on monetizing this trade-off in the form of the social cost of carbon. This object quantifies the total social cost of 1 additional ton of CO2. And it allows policymakers to turn this into an apples to apples comparison so that the costs of mitigating greenhouse gas emissions can be appropriately weighed against their benefits. This is not just economists sitting in a room liking to talk about trade-offs. It's actually how a lot of climate policy is done, particularly in the United States, where many of our policies and our regulations have to pass a cost-benefit analysis legally. And after 2007, that cost-benefit analysis must include the costs and benefits of greenhouse gases. So faced with a Supreme Court ruling in 2009, 2010, the Obama administration instituted the first federal government agency-wide social cost of carbon estimate, which was $52. Our estimate being the total social cost of an additional ton is $52. This estimate came from the best available science and research at the time, and you're seeing a key component from those models that led to that number in the lower left here. This is called a damage function, and it relates total losses of global GDP under different magnitudes of warming on the x-axis. And these 3 models that led to this number were really influential, both in research and in policy. The SEC was used to assess over 80 different regulations over the course of the Obama administration. In 2017, the Trump administration cut this number down substantially with a variety of different subjective choices. And now we are back to that $52 number under the Biden administration with an interim estimate that relies exactly on the science and economics of the 2009-2010 number. That's kind of the story at the federal level in the United States. Many other states within the US use the SEC to assess climate policy, and then other governments as well use the SEC in a similar way, sometimes drawing directly on the science and evidence developed here in the US. So these models have been really important. You know, the creator of one of these models recently won a Nobel Prize, but it's become clear that in the over a decade since these were used to develop the SEC, that there's a lot of updated science and economics that needs to be incorporated into this number. So here's just one quote from the National Academy of Sciences indicating that we really need to improve the database, data behind these estimates. And this is what is currently happening right now as the Biden administration actively reconvenes to assess and update the SEC. One of the most important components of the SEC that we at the Climate Impact Lab are focused on, and that is incredibly important in accurately reflecting climate damages, is the empirical base of those damage functions you just saw. So what you're seeing here is a histogram of data publications that have any empirical data in them sitting behind the damage function. So what you see for each graph is the date of publication of an empirical publication that is calibrating that damage function plotted against time. So we see that in general, these studies are relatively outdated and there's not very many of them. And that stands in stark contrast to what has actually been an explosion of empirical literature in the climate impact space. A recent review that we did shows this really exponential increase in data-driven papers that are estimating climate damages around the world. And currently, all of those studies on the right and those blue bars are being left out of most of the policy landscape. So at the Climate Impact Lab, we're trying to remedy this gap, and we're focused on 2 big goals. First is that estimate of the social costs of carbon from a data-driven approach. We want to use empirically derived estimates using best available science and economics. But most of the talk today, I'm going to be focusing on the second goal, which is to provide hyper-local estimates of climate damages in a sector-specific manner. Of course, we're talking about mortality here today, but we're conducting a similar type of analysis for many different sectors. And by providing high-resolution, location-specific estimates that are sector-specific, we're hoping this helps enable adaptation planning and preparation for future warming risks. So let's look at what this looks like in the context of mortality. The first step in our approach is to collect comprehensive data from as many regions around the world as we can. A lot of prior evidence on climate change damages relies on data that are easy to collect, largely from wealthy, more temperate regions. So this was a large data collection effort to build a subnational mortality record from as many countries as we can. As you can see, there remain really important holes in this map, which we are actively working to fill, but this is the current database sitting behind the estimates that you will see. We then estimate a statistical relationship between the mortality rate and a flexible functional form of temperature and precipitation. So basically, we're using historical events of heat and cold and rain and dry events to see how mortality rates vary under different climate conditions. And we use a set of non-parametric location and time controls to isolate plausibly random variation in the weather. So for example, comparing Chicago to itself in a slightly hotter summer as opposed to a slightly cooler summer. What comes out of this regression is what's called a dose response function, linking deaths per 100,000 to daily temperatures. And what you're seeing in the bottom panel here is that on average, it's one age group that appears to be very sensitive to both extreme cold and extreme heat, and that's the age group above 65. So they see increases in mortality rates both on extreme hot days and under extreme cold. In general, on average across our population, we're seeing basically no statistically significant evidence of response for these other age groups. Now, this gives us one estimate of mortality sensitivity to extreme climate conditions, and in particular here, temperature. We don't see strong results for precipitation, so I'm going to be talking about temperature going forward. But of course, we know that populations are very differentially vulnerable to these climate events. So how can we think about that in the context of mortality? Let's go first to the coldest regions of the globe. What you're seeing on the graph on the right is the effect of a single hot day, 35 degrees Celsius, for this more vulnerable 65 plus age group in the regions of the world that are shown on the map, very, very cold to begin with. Here we're seeing really large impacts. That means these regions that do not experience these days very often are very sensitive when they experience one hot day, don't necessarily have the technologies or the behaviors or the adaptation in place to respond well to that heat event. In contrast, if we move to warmer and warmer regions of the globe, we see that this marginal effect on the right is declining as these populations are more prepared for these events, whether they have technologies or they can adjust their behaviors in response to that heat event to protect themselves from that hot day. So by the time we get to the very hottest decile of the global population, we see a much more muted response to an additional hot day. To formalize that intuition statistically, we use this historical data to then estimate a similar model to the one I showed you before, but one in which that mortality sensitivity to temperature itself depends on different conditions that we see at different regions in the world. So for example, think about this beta coefficient here reflecting the sensitivity of mortality to temperature. We then allow that sensitivity to itself depend on the average climate in a given location to reflect the fact that populations adapt to the climate that they expect, and to log of GDP per capita, so reflecting average incomes. People are more able to invest in adaptive technologies if they have the financial resources to do so. So what comes out of this more rich model is a changing mortality temperature relationship that depends on the conditions in each location. So if we start by going to the poorest and coldest regions of our sample, we see a very extreme response to hot days. These are places that don't have the financial resources to invest in adaptation, and they don't experience these hot days very often, so they're very unexpected. However, if we look within this column but go up in our graph, we see the effect of rising income on this sensitivity. So the fact that this mortality response is being pulled down suggests that higher incomes facilitate adaptation and help protect people against these hot days. Similarly, when we move to the right in this figure, we see again this response on the hot side is declining, suggesting that in locations that are on average hotter, people are more able to prepare themselves and protect themselves against those hot days. This is important if we just think about diversity and vulnerability in today's population, but it's also important when we start thinking about what's going to happen over the coming centuries as climate change, decades to centuries as climate change unfolds. And what these population numbers show you is that in general, we want to be thinking about populations moving to the right and up as they get warmer under climate change and are generally projected to have increased economic growth. Of course, we use a variety of socioeconomic scenarios to project different scenarios of income growth and warming, but in general, we want to think about populations moving up and to the right, reflecting enhanced adaptation to particularly those heat events. So what does this look like spatially? Before I dive into showing you some maps of this differential sensitivity across the globe, I want to point out that current estimates of the social costs of carbon rely on very coarse spatial resolution. So these are two examples, DICE and FUND, that give us at most 16 different estimates around the world. But of course, we think there's a lot more heterogeneity in the vulnerability to climate change. And so we are going to leverage a lot of changing computing and data availability that's happened since the 10 years when the SCC was first developed to provide much more local level damage estimates. We hope this will lead to a better SCC estimate, but also will help facilitate adaptation planning in more localized regions around the world. So here's what these sensitivity estimates look like within the sample of countries that we have mortality data for. So those darker red colors indicate a higher sensitivity to a hot day and a larger increase in the mortality rate for a given hot day. Those red regions, again, tend to reflect colder parts of the world where those hot days are very unexpected. We see the most well-adapted regions are both wealthy and hot, where they're expecting these hot days to happen and the financial resources are available to invest in adaptation technologies. So this is what it looks like within our sample, but the power of this model where we're using location-specific conditions to predict sensitivity in a given location means that we can use projections of income and average climate to estimate vulnerability everywhere in the world, not just where we have mortality data. So here's what it looks like when we generalize that extrapolation across the rest of the world. We can see the same sort of tension playing out between cold and higher income. So of course, as you might expect, cold regions of the world, we're seeing very high sensitivity to heat if those heat events do occur. And while we generally see that hotter places are better able to protect themselves against these heat events, Sub-Saharan Africa is a region where populations are so poor that even though they're getting hit with these hot days very frequently, they're still very maladapted to those heat events. This is what we project the world to look like today. Mortality sensitivity estimated across the world for 25,000 regions. But as we think about the future under climate change, we expect this map to look different as populations get wealthier and hotter. So for example, in 2050, we estimate that most regions of the world are getting slightly lighter. So that means a lower sensitivity to that heat event in 2050 as compared to 2020. This is due both to rising incomes and to a slowly warming climate. This looks even more the case in 2080, and by the time we get to 2100, this map looks much more muted, indicating a much more adapted world for those hot days than we see today. So we want to bring those estimates of differential vulnerability and changing vulnerability through time to project the impacts of climate change in the future. But before we do that, those changing maps I just showed you highlighted large benefits from adaptation. If we had forced populations to stay just as vulnerable as they are today, it's likely damages would look a lot worse. So by allowing populations to invest in adaptation behaviors, as we observe them to do in historical data, we need to also account for the costs of those adaptation investments. If what we project is that a lot like regions like India that are expected to see really substantial increases in hot days also increase at air conditioning adoption, we need to account for that as part of the cost of climate change. I'm not going to go into the details in this talk here, but we develop an approach to infer those adaptation costs, even though, of course, we cannot measure all the many different ways that populations adapt to a warming climate. The basic intuition is that we will assume that people invest in adaptive behaviors and technologies up until the point where the costs of doing so just equal the benefits. So I'm sitting here in Santa Barbara without any air conditioning in my office or my home because it just doesn't make sense for me to invest in that technology, given that I'm only going to experience a couple of days where I would turn on my air conditioner. That's definitely not true in a place like Houston, Texas, where everybody has AC, because the costs of doing so are very much worth the large benefits. So because we've observed those protective benefits, you saw those differential vulnerability under different climates, we're going to use those protective benefits to infer adaptation costs. Happy to answer more questions about this method if people are interested. This now allows us to actually generate projections under climate change because we have a model of adaptation, both the benefits and the costs. Before I get into a model including adaptation, I want to show you a benchmark model in which we do not allow there to be adaptation. So we fix all the regions of the world at their predicted vulnerability today. And what we see is that by 2100, the impacts in terms of deaths per 100,000 of a high emission scenario are incredibly large. This is over 200 deaths per 100,000. If people don't look at mortality data very often as a benchmark, auto fatalities in the United States are about 11 deaths per 100,000 today. So this increase in the mortality rate looks very different if we account for the fact that rising incomes will lower vulnerability. So you can see this gap between these two lines as the benefits of accounting for income growth in the future in terms of mortality protection against heat. Similarly, this curve falls even farther when we account for the benefits of climate adaptation, expecting those hot days to happen as our climate gradually warms. And we can add back in our estimates of adaptation costs to get an estimate of about 75 deaths per 100,000 at end of century. Now, of course, these estimates are highly uncertain. We're very careful to track econometric and climate uncertainty throughout this whole process. And I encourage you to go to our website and download some of these data. And we're doing our best to make sure all of the uncertainty and these point estimates are made available so people can see both what we expect to happen in terms of the mean, but also the distribution for the globe and at a spatially explicit manner. Of course, those global impacts look highly heterogeneous, and we're going to dive into the Asian region in a moment, but I just want to point out when we're looking at the global distribution, we're seeing really stark differences where the large regions of the world are benefiting from climate change because they are saving lives on cold days that are no longer happening under a warming climate. Much of the global south is facing a risk of increased mortality risk under climate change due to increasing hot day risk. In terms of magnitudes, these effects are very large, particularly for today's poor populations and for today's locations that are already very hot. So what you're seeing on the right are leading causes of disease today. And you can see that in the low-income regions and in hot climates today, these estimated impacts of warming are on par with some of the leading causes of death today, such as cancer and infectious disease. So this gives you a bit of a picture of the globe, but of course we want to dive in and see what's happening in the Asian region in particular. So here's a version of the map where we're zooming in on the Asia Pacific region, and we're looking at rescaling this map to look at heterogeneity within this region. And so what you can see is that this region is really a microcosm for that bifurcated world you saw in the global map. In the north and in parts of China and in Japan, we are seeing benefits due to avoided lives being lost on extreme cold days. This is happening less and less under climate change. For most of the rest of the region, we are seeing moderate to severe increases in mortality risk due to exposure to extreme heat. So this looks like a lot of heterogeneity, but what's also really interesting about the Asian region is that the most extreme damages are incredibly concentrated. So here you're seeing in purple, 10 cities, the 10 large of the cities in the Asian region that have over 500,000 people. These are the 10 cities with the largest mortality benefits from climate change, almost all of which are in China, in northern China. In contrast, the 10 cities with the largest mortality damages are highly concentrated in Pakistan and Bangladesh. So let's dig into these estimates a little bit more. If we look at the places that are most at risk, we see that they are dominated by Pakistan and Bangladesh, and that these are places that today are very poor. Even by 2100, we are projecting, this is under one of our socioeconomic scenarios, of course, in the paper we do many others, but these are regions that are not projected to reach very high income levels, even by 2100. That's leading to very large projected damages. These estimates in some of the Pakistan cities amount to an almost 50% increase in the mortality rate relative to today. These also are regions that are very hot, as they are going to be facing even more extreme heat days under climate change. In contrast, we see that the regions that are positively impacted tend to be very wealthy. So this is really a story of inequality, even when we look just within the Asia Pacific region. Most of these cities are very wealthy and of course are very cold because these are the places that are benefiting from those avoided cold day deaths. One region to point out here is Ulaanbaatar in Mongolia, which sort of stands out on this list as not a very wealthy region, but is so cold and baseline that on net is saving quite a lot from projected warming. So just to show sort of why we're seeing these really extreme patterns in the Asia Pacific region, here you're seeing these 230 cities, all of which are over 500,000 people across the region. And you're seeing on the y-axis mortality impacts at end of century against long-run climate on the x-axis. This positive correlation is showing you that on average, it's the hot places that are suffering under warming and the cold places that are benefiting. But what the size of these dots indicate GDP per capita. And so this graph is really showing you that it's the combination of being poor and already being in a hot climate that is really the recipe for really high projected damages under climate change. So that's going to be it for me at the start. I'm going to pass over to my colleague Jiacan. So before I hand over, I just want to highlight that what you've seen so far is a relationship largely between daily average temperature and increases in mortality rate. There's a lot of evidence that other components of the climate also matter for mortality rate. And in particular, humidity is a really important driver of health outcomes under warming. And to date, we haven't really had sufficient climate projections of humidity under different emission scenarios to generate the type of projections that I'm showing you, accounting for humidity as well as the daily average temperature that I just showed you. Luckily, Jiacan is sort of leading efforts in this space to provide those projections, which will help us move beyond the results you just saw and hopefully in the future include the humidity-based estimates that she's going to show you now. So I will pass on to Jiacan and I appreciate your patience and time. Thank you.
Thanks, Tamma. So, can I see my screen? Okay. So for my part, maybe contains two sectors. First, I'm going to introduce how we use the mortality impact result Tamma just introduced to inform the local government on urban planning within a individual city. Here I use the Chengdu, which is a city in the western of China for a case study. And Chengdu is a big city with population over 200 million. And it's also famous as it's the hometown panda. So at Fudan University, I'm involved in a project which is funded by the Chengdu local government. So in this project, climate scientists at Fudan University collaborate with the local government officers to deliver assessment report of climate change risks and also help them to improve the climate monitor system and the impact predict systems. So for the mortality, in this project, we divided the, maybe use a laser point. So we used the whole areas of Chengdu and divided it into two parts. So the blue denotes the planned urban area. So the current urban area is a little bit smaller than the blue areas. And the green denotes the rural regions. So based on the mortality impact result from Carleton et al. 2020, we calculate the impact of climate change on mortality in Chengdu by 2100. The figure on the left shows the deaths over the urban area, rural area, and the whole area of Chengdu for two cases, fully adapted case and no adaptation cases. So we can see the mortality in terms of deaths in urban area is higher than that in rural. And the right panel shows the mortality rate in terms of the days rate, deaths per 1 million. So it suggests the average of mortality rate in Chengdu is lower than the global average in 2100. And if we compared the two cases from fully adapted to no adaptation, it suggests the adaptation can reduce mortality largely, so which encourages the local government to invest on adaptation. So second, I'm going to introduce our recent work about escalating population exposure to heat waves measured by a improved index considering both humidity and temperature, as Tamma just mentioned, in the context of global warming. Generally speaking, people in a place with high humidity feel hotter than in a place with low humidity, even at the same temperature. That's because people can easily to sweat in the place of low humidity to cool the body, but the people in the high humidity place, it's harder for sweat to evaporate because the air is already so moist, so the body doesn't cool down as easily. Therefore, besides temperature, humidity is another important contributor to thermal comfort. Here we use the Webb global temperature as an index to measure the compound effect of both temperature and humidity. As the so we call it WBGT for short, because it has widely used in health guidelines. This table shows the WBGT reference values defined by ISO 17243. And for instance, if for an acclimatized person, if the WBGT goes to 28, the person can only do very light activity, which is lighter than walking. And if the WBGT goes to 33, the person have to rest to keep their make a core body temperature within the normal value. Generally, the WBGT is calculated by the weighted sum of 3 variables. Well, TA is the dry bulb temperature, which is the temperature we use in daily life. And the TG is the globe temperature, measures the temperature of radiation, and the TW is the Webb temperature, which is the lowest temperature to which air can be cooled when evaporating waters into the air at constant pressure. And in a shaded conditions, generally the TG is equivalent to TA, so the WBGT can be simplified in this version. However, in the climate models, which we use to project future climate changes, the WBGT is not a common output. So we have to calculate it with other variables. Here we develop a method to calculate the Webb temperature, which we call it isobaric Webb temperature, by numerically solve this entropy balance equation. And by this method, the Webb temperature can capture the physical process of cooling body through perspiration. So this chart shows our working flow of this work. Basically, we're using the physical variables produced by climate models to calculate the WBGT simplified version in response to global warming. And then we engaged with the global population data to obtain the world population exposure to extreme WBGT. So here are our results. These figures shows the change in frequency of exceedance in response to the increasing of global mean surface temperature at 1 degree C to 4.5 degrees C. Each column shows the exposure to the different intensity of the humid heat waves using different threshold for the WBGT. So these 3 thresholds is determined by the WBGT reference values. Say for the 31, WBGT means people can only do very light activity, and 33 means people have to rest to maintain their core body temperature within the normal value. And the 35 is very extreme case, which is calculated from historical maximum value in observations. Because currently our climate is in a global mean surface temperature increase about 1 degree above the pre-industrial level. So we can regard this role as our current climate. You can see for the less intensive heat extremes, most area of the Asian Pacific regions are affected, say the South Asia, Eastern China, Middle Chinese Peninsula, and most area of the Australia. And for the very severe heat extremes, only the Bangladesh and Pakistan is affected. So this is is consistent with the mortality results Tamma just showed. And if the global warming continues when the global mean surface temperature increase to 45 degrees C, you can see most areas, except for the Tibet Plateau and some area in Mongolia, will be affected by the humid heat extremes, and even for the very severe case, say the Western Southern Asia and Eastern China and the western part of Australia will be affected. Here we look at it from a different angle, say for an individual city. Here we use Shanghai as a case study. If the x-axis is the different threshold for WBGT indicate different intensity of humid heat extremes, and the y-axis is the frequency of exceedance in units of days per year. And if we take a look at the WBGT over 33 degrees C, this intensity of humid heat wave, for example, if the global temperature goes up to 1.5 degrees C, the frequency will be 1 day per 70 years. And if the global mean surface temperature increases 3 degrees C, this kind of extreme will appear 1.6 days per year. And if it goes to 45 degrees C, it will averagely estimate will be 12.4 days per year. So that will be very dangerous. And here we show the population exposure to extreme WBGT. And the left column shows the regional average of the population exposure over the Asia Pacific area. Upper panel is the population times days, and middle panel is the population exposure in a frequency of over 1 day per year. And the bottom panel shows the population exposure in the frequency over 1 day per decade. And on the right hand side, here we show the map of the population exposure at the frequency of over 1 day per decade at different intensity of humid heat extreme, also in response to the global warming. And if again we take the intensity of WBGT over 33 degrees C as an example, for global mean surface temperature increase 1 degree C, there will be 754 million people exposed to the extreme humid heat. And from the map, we can see the people all located over the Pakistan, Bangladesh, and northern part of the India. And if it goes to 1.5 degrees C, the population exposure will be 879 million, and 2 degrees C, about 1 billion. And if it goes to 3 degrees C, it will close to 2 billion. And besides the northern part of South Asia, the South China and also the Sichuan Basin and the Chinese Indo-Chinese Peninsula will be affected. And also in the 45 degrees C of increase in global mean surface temperature, the population over the Asian Pacific region exposure will be almost 2.7 billion. So as Tamma mentioned that right now especially for the Asian Pacific region, we not only for the mortality impact, we should not only focus on temperature, maybe humidity is an important variables we should account for. And looking forward, we are going to implement this new index into our impact result. So then I will pass it to Tamma for other sector impacts and also for the conclusion. Tamma, I will stop sharing.
So just to wrap up, I think you can go to the next slide. I just want to pull us back together and you know, of course, we've been focusing on health today, but as I mentioned at the beginning, at the Climate Impact Lab, we're focused on implementing a similar type of approach across many different sectors of impacts and trying to build those estimates together into a social cost of carbon, but also to provide location-specific decision makers with sector-specific information across many different sectors. Jiacan, if you can flip the slide, please. Jiacan, can you flip the slide, please?
Oh, okay. So
I'm not
next slide.
Seeing, yeah, next slide.
Is this what?
I'm not seeing the bar graph. I'm sorry.
Oh, can you see my screen right now? Oh, sorry, my screen sharing is paused. Sorry.
That's okay.
You'd
think after 2 years on Zoom, we would have mastered this, but thank you everybody for your patience. What I'm hoping to show in a moment is some results for estimates of the damages from a ton of CO2 in multiple different sectors that we've been studying, including mortality, and how those estimates compare to current estimates that sit behind the US social cost of carbon. If you'd like, Jiacan, I'm happy to take over the reins again, and I can share my screen if that's easier.
Okay, I'll still share.
No problem. Okay, so here what you're seeing is a comparison of some of our estimates for different sectors of the economy as they compare to the current social cost of carbon. So on the left, you're seeing this gold bar is the current social cost of carbon that is intended to include all sectors of impact. That's about $52 under the interim value from the Biden administration. And on the right, you're seeing in blue our estimates for a variety of different sectors, and as they compare in gray to one of the models that provides a sector-specific breakdown that feeds into the gold bar. So these gray bars are from the fund model, which is one of the three models making up that gold bar. So the key take home here is that in many of these different categories, we're getting both very different magnitudes from prevailing evidence and in some cases, even different signs. So for example, with energy demand, we project slight decreases in energy demand for every additional ton of CO2, largely due to savings on heating fuels in the future. In contrast, prior estimates suggested that the energy demand response may be one of the most important components of the social cost of carbon. Reflecting the estimates you just saw today, when we monetize those mortality projections and turn them into a social cost of carbon by pulsing the climate with 1 ton of CO2, we see that our estimates are incredibly large when compared to the estimates that sit behind the current SCC. For labor disutility, this is not something that's even included in the existing SCC. And for agriculture, we are also obtaining an estimate that is larger and even of a different sign than prevailing evidence. This is sort of an aggregate view of what these estimates mean across different sectors at the global scale, but to highlight some of these sector-specific impacts, these in particular are available on our website if people are interested in looking at what's happening in their region. But here's an example of what we see for one particular sector in different regions of the world. So in the case of electricity consumption under climate change, we find that there, again, are a lot of heterogeneity around the world in what climate change means for each country. So for example, in a place like the United States, we're seeing that the impact of a high emission scenario on expenditures of electricity is very small relative to current consumption, only 2.7%. In China, it's a little bit larger, but still a very modest response from climate change. But there are regions, and in particular, there are regions in this Asia Pacific region that actually experience a very large change relative to current consumption. So India, we're looking at 145% increase in electricity demand relative to today. In Pakistan, it's 170%. So again, this is just sort of a window into what some of our results are for other sectors. And we are looking forward to questions and definitely point you to our website, where as our papers come out, we're trying to make these data as readily available as possible. Thank you all so much for your time, and look forward to answering questions.
Great. Thank you both so much for packing so much information in a short presentation. Really appreciate that. So now we'll move to some questions for both of you, and you can decide who would like to speak about what. One of the questions that come in: how do you account for limited income growth and therefore adaptability due to warming?
Great question. So all of these estimates, including the one I'm showing on this slide, include one projection of GDP per capita at the country level. We downscale that to higher resolution than country level, but this is like one scenario of what GDP per capita might look like going forward. There's an entire modeling community that works to build these scenarios, and we show results for a variety of different scenarios. But I think what you're getting at is the idea that it's possible that climate change progresses and that actually lowers these projections of income per capita, which should, according to our estimates, increase vulnerability in many regions of the world. So my answer is twofold. One is that in our paper, which is published, which is publicly available as a working paper, you can see how these results vary across different socioeconomic scenarios. So we include results across a variety of them. I didn't want to bombard you with a whole host of maps and time series here, but as you may imagine, of course, different socioeconomic scenarios lead to different estimates of vulnerability in different regions of the world, and we do show that in the paper. But my other comment is that if you're thinking about endogenous effects of climate change on income, so when I generate a projection here for a high emission scenario, shouldn't I also imagine that incomes are being affected by those high emissions through many other channels of impact, and then account for that in vulnerability? And I think that's a really important comment, and it's not currently included in these estimates. However, I would say that what we've added to the paper is a comparison of the differences in these socioeconomic scenarios as they compare to existing estimates of the impact of warming on GDP. And basically, if you just look at the variance across these different scenarios, that's just about as big as the variance in projected damages from warming. So I think looking at the scenario, the breadth of impacts across scenarios gives you a really good picture of what the sort of breadth of possibilities might look like, even if we were to endogenize the effects of income growth on vulnerability. But thanks so much for the question. It's a really important one.
Of course, thank you. Another and somewhat related question. You talked about some specific sectors. This question is, how much will agricultural production in particular be impacted? And do you have estimates of how much world population it can support based on those impacts?
Yeah, great question. So I do have a little agriculture bar on this slide. That paper just got sent off to review, so it's not publicly available yet. I will say there's a large body of evidence on the agricultural impacts of climate change within Asia and across the globe. Probably more than any of these sectors, this literature is probably the richest, both in terms of economists and agronomists and people running experiments in giant greenhouses. There's just a massive body of literature working on this problem. We think our estimates are particularly valuable because we apply sort of two big pieces of the philosophy you saw today. So a really big data collection effort. We're measuring how actual farmers respond to climate events with a really large database from across the world and many years of observed records. So really trying to capture very rich diversity and responses from actual farmers on the ground as opposed to a lab experiment. And then the second component of what we think is really novel about our work on agriculture is that we're measuring these changes in vulnerability. So I just highlighted a lot today about how vulnerability looks so different in different regions of the world and is projected to be different in the future for mortality. We see the same thing with agriculture, where adapting to your climate, having higher income to invest in different seeds can really change those responses. And so our estimates are also capturing that. Well, I can't, release the paper to everyone right now. I will say that our estimates are looking at like somewhere around 20% for many major crops of loss under a high emission scenario once you account for a projected adaptation. And I think those numbers are somewhat similar across the Asian region as well. Again, the Asian region looks sort of like a microcosm of the globe with a lot of heterogeneity from north to south and rich to poor. But yeah, the estimates are looking at somewhere around 20 to 30% of yield losses in many major crops, which of course has really big implications for the global economy, for local economies, and for food security. And hopefully we will have that paper out soon and you can open it up yourself. Thanks.
Great, thank you. Another question, you pointed out that the 65 plus, of course, are the most sensitive. And Asia's very heterogeneous, you pointed out, in many dimensions. Of course, it's in the already high income places that have the greater ability to adapt that you have a higher share of the population that's in that most sensitive age category. I just wanted to invite you to talk a little bit about that situation, if you'd like to.
Absolutely, yeah. I'm not sure what the right graph is. Maybe I'll focus on this one. It's a great comment. So I think this question and comment is pointing to two things. One is sort of the distribution of people in those three age groups differs across the globe. There's probably a lot more people in the 65 plus age group in wealthier economies. There are. But also that there's some heterogeneity within that 65 plus age group, which is also true. There's a lot more people in their 80s in the US than in other developing countries. And so my answers to that are slightly different. So on the above 65 age group, we unfortunately just don't have rich age demographic information for all of our samples. So we couldn't estimate differential sensitivity to warming in a finer age bin resolution above 65 for the whole sample. We have really rich data from Japan, actually. And so we have done a more detailed analysis in Japan, and it looks like even within that age group, as you may expect, it's the oldest that are the most vulnerable. So vulnerability sort of like continues to march upward within that 65 plus age group. And so there is definitely heterogeneity that we are missing by only being able to look at 65 plus. But if you are concerned about the age groupings within those three groups, all of the projections that we conduct are conducted separately for these three age groups and then aggregated together at the end. And we use those socioeconomic projections, which include demographic transitions, to allow populations to move between those three age groups as projected by the demographers that build those models. So I'm not in the business of I don't know how accurate those models are or whether you would agree with them, but what we are doing is capturing that heterogeneity in demographics and allowing that demographic change to unfold as projected in the scenario, so that you do see a lot of populations becoming older and then moving more of their population into that 65 plus group as incomes rise into the future. So that is accounting for sort of in the background, and happy to point you to the paper in the appendix where we break down a lot of these results by age group if you're interested to see, how much of the average effect that you're seeing on this slide is driven by that older age group versus other age groups.
Great, thank you. Another question has come in about how the modeling teases out various different effects on mortality. So the question is, how did you separate out heat mortality from cardiopulmonary mortality due to increased particulate pollution from coal burning, for instance?
Yeah, great question. So these estimates are definitely not claiming to account for or include the enormous burden of air pollution on human health. So our intent with our regression approach is, like you said, the question asker said, to isolate the role of temperature from those other very important factors. And I know there's lots of other people working on quantifying the importance of local particulates on mortality. And the way that we do that is through a really well-developed body of statistical work in climate impacts analysis that allows us to estimate random variation in the weather. And so back to sort of our thought experiment from that regression, and we're using non-parametric controls to compare the same population to itself under slightly different climate conditions. And so you're controlling for sort of average particulate matter in a location, for gradually changing particulate matter, and just isolating the role of a couple more hot days or a couple fewer hot days. And so that approach allows us to separate temperature from other potentially correlated variables like air pollution. So I think you should think about those local particulates as like layering, the impacts should be layering on top of the estimates that you're seeing here, and it could have really important quantitative impacts on top of what you're seeing in these projections.
Yeah, I agree with Tamma, and actually I think it's hard to basically based on the physics or the how to separate the heat and the pollution effect on the disease. But right now we are collaborating with some scientists from the public health, and they have some record of the disease, and to maybe they correlate with the weather conditions such as heat and population, and they are doing some mechanisms examination to try to find the distinguished characters of the heat under some like the cardiopulmonary. They may have different features between heat and air pollution, and then right now we are trying to figure out if some ways to distinguish these two effects on the same kind of cardiopulmonary disease. And this is one way. And the other thing is that we found both heat and air pollution have the effect on the human health, and also sometimes heat will increase the impact of the air pollution. So probably it's also a good way to look at them, the like compound effect of both heat and air pollution on health.
Thank you. Yeah, Professor Yuan, maybe to follow up also with you, a question about your work in Chengdu or elsewhere, unrelated specifically to the technical aspects of what you talked about, but more broadly, you said you've been working with policymakers and local adaptation policy. Could you share with us any thoughts? What's the most common question you get from policymakers and reaction you get from policymakers in processing this research, thinking about the use of social cost of carbon and these damage calibrations in their specific policies?
Yeah, that's a very good question. Actually, in our project, we mainly collaborate with the local officers at a technical level. So we are not actually engaged with the policy making process. So we just applied some suggestions about how future climate change will be and what the risk we will expect. Basically for the very, I think right now China is is approaching the carbon neutrality at this moment. So government is like more focused on how to mitigate the carbon emission, and maybe using some policy regulations or using economic marketing. So there is a debate, but maybe both ways will be applied in the like cut the carbon emission in the future. So I think in terms of the social cost of carbon, it will provide estimation, especially with the heterogeneity in China, it will provide detailed information to suggest the local government how to decide the price of the carbon emission in their economic activity. So it will provide some guideline for them. But right now, it's just the suggestion from the climate impact lab side. In China, there are also some economic organizations that will like using other methods to calculate the social cost of carbon or to decide the carbon price. So I think they provide multiple, like from different angles, provide multiple guidelines for suggest the government how to decide the carbon price and to do it in a right way. But right now, I'm not actually assessing this part. I just cannot give very clear things about how they will imply our suggestions. So I don't know how to answer.
Well, thank you. That's very interesting. That's what we researchers do, right? Provide the evidence and go from there. Thank you. So another question, just in general, what do you think are the most important knowledge gaps in this area? What are the most urgent needs in terms of, is it further data collection or other ways of modeling? What do you think are the most important knowledge gaps going forward about the health impacts and broader livelihood impacts in Asia and elsewhere of climate change?
I'm happy to take that. I think there are, I had a good answer until you added on the end of your questions. Before we get to, in terms of which impacts, I think we are finally at a point, both with this work on mortality and with other sectors, where we have this sort of local level information on projected risk under different emission scenarios and different adaptation scenarios. And I think, our hope is that it's useful and used. And to me, I see like what the biggest sort of gap and thing that I'm thinking a lot about going forward is it's one thing for us to publish papers, but it really making this useful. And we've got a great team trying to do that and get this information into the hands of people who can act on it. But I think a big unmet need right now is this next step of translating this information, which really wasn't available until we were able to provide this local level information, which is really important for adaptation planning. How do we get it into the hands of people who can help make better adaptation decisions, and in particular, help those who are being most negatively impacted? This story within Asia that we're seeing on the map, within the United States and across the globe, is just one so much of equity and unequal impacts that I think what's really hanging over my head is how do we get this information into the hands of people who can do something about it, and all the while ensuring that those who don't have the resources to respond, who are projected to be the most damaged, are helped. And so, I'm an economist, I'm not a political scientist, that's sort of beyond my domain of how exactly that's going to work, but I think we're working really hard to make sure our data can get out there, and I think that's how it does so and how people can actually respond to it. I think, I'm hoping is an area where we can contribute going forward. And then I'll just tack on and then pass on to Jiacan. I think the big next step and unanswered question sitting in my mind is the other health impacts that are not, this is mortality and temperature. For, as Jiacan pointed out, it doesn't even include the effects of humidity. And so there's a lot more to do on the health impacts. And I think the really big one, particularly for developing countries, are vector-borne diseases. And there's definitely some estimates, and there's a lot of people working on it, but I think providing the same type of like high resolution projections under different emission scenarios for the regions where these key vector-borne diseases are likely to be affected by warming, I think that's a really important area to move into next. Jiacan, I don't know if you have any other next steps answers.
Yeah, I think you give very good answers. So I think at the public level, we should also do some improve their acknowledgement on the climate risks, besides the academia and the governance level. So I think the another gap is how do you knowledge the public to understand the climate risks, although it's a very small progress. There is a long time to reach the risk, but people should prepare earlier. And especially right now, the extremes is more frequency and more intensive than before, and then people may not expect it. So if they have those knowledge in mind, they may have some intuition to protect themselves when they face the extreme weather, which is maybe haven't happened in the history.
Great, thank you. So for our audience, if you have any final questions, want to ask those. The final question we have here now is a question if you have advice for young researchers or any homework to assign. Stanford University, as you may or may not know, is starting a new school of sustainability and trying to foster the research, but also have impact across the region and the globe. Your team, as you mentioned, is extraordinary, interdisciplinary, international. Do you have any advice about how to have effective teams working on important issues and having the translation into impact?
Oh, that's a great question, and very exciting to hear that about Stanford starting a new school. I'm in an interdisciplinary department here at UC Santa Barbara, and love that my colleagues are hydrologists and legal scholars and very diverse from my own research interests. I think that everyone has very different perspectives on interdisciplinarity. I think what makes this team work really well, if you're looking forward toward a career in interdisciplinary work, particularly within sustainability, is that we all have very strong disciplinary expertise, but are invested in spending the time and energy and learning to speak each other's languages. So we've got economists, computer scientists, Jiacan is a climate scientist, so we're coming to the table with pretty deep disciplinary expertise, but willing to jump across the table and try to figure out how somebody else thinks, which is quite a different model than in some cases where people actually invest in a skill set that is very diverse across multiple disciplines. I think teams can work in different ways, and my experience is that this team has been very productive because of that deep disciplinary expertise and the willingness to work together. So it's one model, and I think it's working well. And I personally would encourage, like, sort of, if you're a young scholar trying to think through, how much to build one disciplinary skill set or not, I do really think it's really valuable to come to these interdisciplinary tables and questions that inherently link across disciplines to really have training in an area that your value coming to the table and how you can contribute to these big complex problems. And I think that's hard to do, but I think that's part of why our work has gone so well. And to add to that, I am not good at building a website and reaching policymakers, and so we also do have team members who help us try to get this work out into the world and in an accessible way, and on a website and on podcasts. And so I do think also there's only so many things each one of us can do, especially if you're trying to be an academic. And so finding people that can help you do that policy outreach and do that effectively is really valuable. I'm not on Twitter. People tell me that Twitter is the way you can do that as an academic. I don't know, but maybe that's the solution. But I think it's been really wonderful to have communications colleagues who really help us figure out how to change our language and our way of presenting to reach diverse communities.
Definitely, Tamma did a very good conclusion on this question. So I just want to add a little bit. Say I'm very feel exciting and almost excited when I'm working in an interdisciplinary team, and I feel I learn a lot through the collaborating process with other scientists and economists, and also we approach in our team we also have people from industrial. So in this, so it's not only the interdisciplinary, it's also across the industrial and academia. So then we can understand what people need in in the life, and we can do like our output more applicable. And also we are a international group, so people remotely working together from China, from Paris, from France, and also from Eastern and Western United States. So, and we also have a like very effective way to working different times, the working at the time differences. So I think that's a very young, energetic, and magic team. So I'm very proud of in it, and hopefully the this kind of model could be and then our results could affect more people in the world.
Wonderful. Well, thank you both so much for sharing, for your research to begin with, and for sharing it with us. We hope to have you both here at Stanford APARC sometime in the future. And thank you again so much for presenting today.